Yes, hi everyone. So welcome back. So today we have a question from Lindeman theory of unimolecular reactions. So the question is, according to this theory, the observed order at very low concentration is. Okay. So before that, we should understand what the rate equation is and what the concept of Lindeman's unimolecular reactions are. Okay. അപ്പോൾ ഇതിൽ അവർ പറയുന്നത് ഇത്രയേ ഉള്ളൂ that the driving force or the energy to cross the activation barrier for the conversion of, let's say, a reactant A to product, അത് വരുന്നത് through collisions ആണ്, effective collisions. Okay, so let's say you have A, which is a reactant. It will collide with another molecule of A, and it will give us the excited state of A plus the other molecule. Okay, so energy is transferred from one molecule to the other. So if we draw a profile, energy profile diagram, this, let's say, is the position of the reactant. It will get excited and reach to this position A. And upon reaching this position, it can take two pathways. Okay, either it can come back to the initial state itself, like A plus E star will give us back our reactant molecules, or it can decompose. It can decompose to form the product. That is, A star can be decomposed to form the product. So if we summarize this, the way we can write this is A plus A star is under an equilibrium condition. Sorry, A plus A is under an equilibrium condition where it is giving us A star plus A, correct? And then this A star will degrade to form the products. So let's say this rate constant where A star was being formed is K1. Let's say A star, which was being deactivated to the initial form of the reactant, അത് K2 ആണെന്ന് വിചാരിക്കുക, and A star becoming product K3 ആണെന്ന് വിചാരിക്കുക. Now it is very easy. We have to find the rate expression, correct, where it is not mentioned which is the rate determining step. So as we know that this is fast and this is quick, as we know that this is fast comparatively because it has to attain stability, it has to attain the equilibrium. So this would be the rate determining step. Okay, so what we have here is rate is equal to dp by dt in forms of the differential equation, and that would be equal to K3 into P star. Now, we cannot incorporate the concentration of A star in the rate expression because it's an intermediate. It's an activated state whose concentration നമുക്ക് കാണാൻ നല്ല ബുദ്ധിമുട്ടുണ്ടാവും. Correct? It's not practically possible. So we'll eliminate this A star and we'll substitute the expression for A star from steady state approximation. Correct? So let's say this is step number 1, 2, and 3 respectively. We know that the changes in the concentration of the intermediate with time, that is equal to 0 according to SSA, correct? This is from SSA because SSA what you have is a transient existence. Okay, so from this, how will you write the expression? At the step pillar, A star is being formed with rate constant K1. So K1 into concentration of A to the power 2, because we have two molecules here. And then in the next step, it is being decomposed. Correct? Step number 2 are the decomposition with rate constant K2, and the reactants are A star into A. And in the final step also, it is being decomposed to P, which is our product with rate constant K3. So this is how it will be. You can rearrange this. Upon rearranging, the expression that you will be getting is K1A squared is equal to K2 concentration of A plus K3 into concentration of A star, and concentration of A star is equal to K1 concentration of A to the power 2 divided by K2A plus K3. Now this is the expression for A star, which will be substituted here. Correct? So the expression for rate according to the Lindeman theory, this is important, that is equal to K1 K3 concentration of A to the power 2 divided by K2 concentration of A plus K3. So this is our expression of the rate for unimolecular reactions according to the Lindeman theory. Important. But the question that they have asked is, what would be the order of the reaction at very low concentration, very low concentrations of A? So whenever such comparisons are given, always we have to check the denominators, always. Okay, so what is given in the question? The concentration of A is very low. If the concentration of A is very low, K2 into the concentration of A, that will be very low. Correct? So if you compare these two terms, ഈ രണ്ട് terms നമ്മൾ compare ചെയ്യുകയാണെങ്കിൽ നമുക്ക് കാണാൻ പറ്റുന്നത് K2 concentration of A, that will be less than K3. Correct? Now if you apply these conditions here, നമുക്ക് denominatorൽ നിന്നും K3 നെ മാത്രം ഉൾപ്പെടുത്തിയിട്ട് you can neglect K2A. Why? Because the value is very low. Correct? So upon doing that, K1, K3, concentration of A to the power 2 divided by K2A na nammal neglect cheyana because the value is not that significant. Adinte value koravana. So you will get like this. Correct? Upon further simplification, what you have is rate that is equal to K1 into concentration of A to the power 2. എങ്ങനെയാണ് concentration of A depend ചെയ്യുന്നത്? It's following the second order kinetics with respect to A. And that is the answer. Answer is the order of the reaction is 2. Option B. Okay. So this was asked in CSIR 2011. Similar questions have been even asked for GATE, and further questions will be posted in the upcoming days. Okay. Thank you.